Everyone, we are back and we're going to do the FRQ portion of the Unit 9 exam review for AP Chemistry. So we have two FRQs today. We have a long FRQ and a short FRQ, and we're going to do them both. So I just came from doing the multiple choice one, and I felt like I really dragged. I felt like I really yapped a lot on that one. Let's try and be a little more concise and brief and clear with the FRQs and try and get this done in a reasonable time. All right. Starting off, looks like we have a galvanic cell, just our standard zinc and copper galvanic cell. Answer the following questions related to the standard galvanic cell represented in the diagram above. The reduction half reactions are given in the table below. So we have copper 2 plus and zinc 2 plus as our two ions, our two solutions. Write the net ionic equation for the overall reaction. All right, we have to flip one of these. The one that we're going to flip is the one that when we add the voltages together, it becomes a positive voltage. We're going to flip the zinc half reaction. I'll stop doing that. We're going to flip the zinc half reaction. We do need to flip one of them so the electrons cancel out. And then we are going to add together those voltages. So we do 0.34 plus 0.76. We get 1.1 volts. Oh wait, that's not what we're trying to find, but that's going to be the next question anyway. 1.1 volts. We need the overall net ionic equation. When we flip to these two, we're going to get copper 2 plus. Let me just write this down. Zinc yields zinc 2 plus 2 electrons. The electrons are going to cancel out, and we get copper 2 plus solid zinc yields solid copper plus zinc 2 plus. The voltage is going to be 1.1 volts. I'm not just going to write 1.1 volts because, whoa, look at that. We have to include, we must show work with our answer. So let me just not put 1.1 volts. Let me put 0.34 plus 0.76 is equal to 1.10 volts. That would be correct rounded to sig figs, the way that addition significant figures work. Calculate the delta G in kilojoules per mole for the cell. All right, delta G, we're going to use the equation that says delta G is equal to negative N times F times E. That is on your equation sheet. Let's go to your equation sheet and see where exactly that is. That is going to be down here where the delta G equations are. That's this equation right here. I know it doesn't write a delta G explicitly, but delta G is equal to negative NFE. F is Faraday's constant, which is right here, 96485. So delta G is equal to negative NFE. We know that F is 96485, E is positive 1.10 volts, N we haven't talked about yet. N is how many electrons are getting transferred, how many moles of electrons are getting transferred for mole of reaction, and we know that that is going to be 2. It's 2 moles of electrons being transferred. So it is a 2, and if we do that calculation, 2 times 96485 times 1.1, we get an answer of negative 212,267. That's going to be, however, in joules per mole. Now, the reason it's in joules per mole is if we go back to the equation sheet, man, I did this a lot in the multiple choice. I kept on going back to the equation sheet. And if we go to the top of the formula sheet, the part that no one ever looks at, up here, you are given that a volt is a joule over a coulomb. The important part there is joule. So volts are in terms of joules, not kilojoules. We are going to have to convert into joules or into kilojoules from joules because we're asked to report this in kilojoules per mole. So that's going to be negative, and then we're going to round to 3 sig figs, negative 212 kilojoules per mole, which is the correct answer. Accidentally hit the this thing. All right. The following diagram on the left represents the copper nitrate solution in the half cell before the galvanic cell starts to operate. In the following diagram on the right, draw a representation of the solution in the same half cell after the galvanic cell has been operating for some time and is still producing a voltage. So if we look at our overall reaction here, what do we notice what's happening with the copper ion? We are using up the copper ion. It's part of the reactants. We're taking solid copper or we're taking copper ion and it is being reduced and it is turning into solid copper. So we should be drawing a solution with less copper ion in it. I don't think we have to draw the solid. It doesn't indicate that. So we have 4 copper 2+ ions. Let's draw 3 copper 2+ ions. So there. The other thing we need to account for is that it needs to be charged balanced. That's why the spectator ions flow. So notice how for every 1 copper 2+, we have 2 NO3 minuses. So the left is charge balanced. We need to draw the right to be charge balanced as well. We're going to draw 6 nitrate ions. You can also draw some, what is the salt bridge soaked in? Does it say? Oh yeah, it says KNO3. So you can also draw some Ks in there, but just make sure it's charged balanced. I don't know if this was a 2-pointer. I don't have my answer key with me. So, but maybe this was a 2-pointer and you got 1 point for drawing less coppers, 1 point for making it charge balanced as well. Assume that the mass of the copper electrode changes by X grams in a certain period of time. Write a mathematical expression for the change in mass of the zinc electrode during the same time period. For example, for every 1 gram that the copper electrode changes, the zinc electrode changes by X amount of grams. Okay, so it's kind of a weird question, the way that this is worded, but all we're being asked to do here is a little bit of stoichiometry. So if our copper electrode changes by 1.0 grams, we're just going to do the stoichiometry to see how much the zinc electrode is going to change. Now we're going to need the molar mass of both copper and zinc to go from mass to mass. Going to our periodic table, copper is 63.55, zinc is 65.38. All right, let me see if I can remember those numbers. 6355, 6538. 6355, 635. Shoot, copper. We'll just do one at a time. Copper is 63.55 grams per 1 mole. According to our balanced reaction that we made over here, for every 1 mole of copper, we get 1 mole of zinc, so it's a 1-to-1 mole ratio. So 1 mole of copper, 1 mole of zinc, and then zinc was 65.83 grams. We're going to double check that. I don't think I got it. 63.55, 65.38. What did I put? This is hard, switching back and forth. I already forgot it again. Was the 3 before the 8? I don't know. 8.3, where was it? 3.8. 3.8. There's 3.8. I'm in shambles. Now my pen won't erase. All right. Let's do that stoichiometry and see how much zinc that we use up. So it's just going to be 65.38 divided by 63.55. We get 1.03 grams of zinc for every 1 gram of copper. So the ratio is really 65.38 to 63.55. But that's it's kind of hard to see what's happening there. What's happening is for every 1.0 gram of copper that increases, 1.03 grams of zinc decreases, goes down, because we're using up the solid zinc according to this reaction. And that's good enough right there. All right, moving on, for the standard cell, the copper 2 plus half cell was made with 1 liter, 1 molar copper 2 nitrate. The zinc half cell was made with 1 liter, 1 molar zinc 2 nitrate, pretty standard. The experiment was repeated, but this time the copper half cell was made with 0.5 liters of 2 molar, and the zinc half cell was made with 1 liter, 1 molar. So the zinc half cell is not changing. It's 1 liter, 1 molar before, 1 liter, 1 molar after. The copper half cell is going down by a factor of 2 in the volume, so it's instead of 1 liter, we have 0.5 liters, but it's increasing by 2 in its molarity and its concentration. Ultimately, that means the exact same moles of copper. Is the cell potential for the non-standard cell greater than, less than, or equal to the value calculated in part B? Okay, there's an equation that's going to help us with this. The equation on the equation sheet that helps us with this, if we go to the equation sheet, is the one that compares delta E to Q. So moving down, my laptop doesn't want to work, but okay. We're looking at this equation right here. E cell is equal to the voltage of the standard cell minus RTNF ln of Q. Let's go ahead and translate that and write that down in this portion. And the reason why is because we have to justify. That's the best way to justify with this equation. So E, I'm going to label this as the new voltage is equal to the E at the standard cell minus RT over NF times natural log of Q. So what that means is that if Q is greater than 1, we are going to go down in voltage. If Q is less than 1, we're going to go up in voltage. Because here's our old voltage, which was 1.1, right? 1.10. All of this stuff right here is positive. And if Q is greater than 1, that means the natural log of Q will be a positive, because the natural log of any number greater than 1 is a positive. We're going to be taking 1.1 and we're going to be subtracting a positive, which means our cell potential is going down. If Q is less than 1, any number, if you take the natural log of a number less than 1, you will get a negative, which means we will be subtracting a negative, which actually means we're going up in voltage. So it's all about just finding Q. If we go back up to our reaction, our Q expression is the concentration of zinc divided by the concentration of copper. So the Zn2 plus times the concentration, or divided by the concentration of the copper 2 plus. And we will get the zinc is 1, concentration is 1, the copper's concentration is 0.5. 1 divided by 0.5 is 2. Q is greater than 1, and according to this equation, if Q is greater than 1, that means we're going to be subtracting a positive, which means the cell potential will go down. Cell goes down. And remember, when it says justify, you are always welcome. You are always free to justify via math. We did math here. This math really helps with our justification. I'd probably say something a little bit more since Q is greater than 1. But we use the equation. This is good justification here. The cell potential is going to go down. In the experiment, if the experiment is repeated with the copper electrode replaced with the copper electrode with twice the mass, will the initial cell voltage be greater than, less than, or equal to the initial cell voltage in the initial experiment? The voltage will not change. What changes the voltage compared to the standard cell are the concentrations. It's the Q. And remember, solids do not go in Q expressions. We learned that in Unit 7 when we learned what Q expressions are. We don't put solids in there. So changing the mass of the solid is not going to affect the voltage because the solid mass does not impact our Q. The solid amount does not impact the Q. The only time the solid will impact the voltage is if we like run out of solid or we don't have a solid there. Then the battery just doesn't operate and the voltage is 0. All right, moving on to FRQ2. A student investigates the reaction between Ag and HNO3, represented by the equation above. Predict the sign and entropy change delta S for the reaction. Justify your answer. All right, so predicting entropy change, I see that we're going from no gas on this side to gas on this side. Gases have way higher entropy changes than any other state of matter, way higher absolute entropies. Which means we are going to be increasing entropy here. We are getting way more random, way more chaotic, a way higher entropy due to the fact that we are producing gas. So we're going to have a positive delta S due to producing a gas. Something along the lines of that, which is NO. Using the information in the table below, calculate the value of the enthalpy of the reaction in kilojoules per mole. We're given a table of enthalpies of formation. Whenever we're given a table of enthalpy of formation or standard entropies or absolute entropies, you should be thinking products minus reactants, and that is what we're going to do here. The enthalpy of the reaction is equal to the sum of the enthalpy of formation of the products minus the sum of the enthalpy of formation of the reactants. So let's set this up. Delta H is equal to, we have 3 silver nitrates, so 3 times -101. We have 1 NO, so NO is 90. We have 2 H2O liquids, so 2 times -286. Those are all of my products. I'll close that parentheses. I usually like to separate products and reactants with brackets. The reactants is we have 3 solid silvers. Now solid silver is not here. Oh no, what are we to do? Let's give up probably. No, that's just a joke. Don't give up, because the reason they don't give you the enthalpy formation of solid silver is because, remember, solid silver is already formed, that is in its natural state, so it doesn't have an enthalpy of formation. Its enthalpy of formation is 0. You don't need energy to form solid silver when it just starts off as solid silver. So the answer to the solid silver is 0. So I guess we can just write 3 times 0. And then we have 4 nitric acids here, so 4 times -207. We're running out of room here. Do that calculation. All right, 3 times -101 plus 90 plus 2 times -286 minus 4 times -207. And we get an answer of positive 43 kilojoules per mole. We are in the right units since all of these enthalpies of formation were in kilojoules per mole. Based on your answers to part A and B, is the reaction more likely to be favorable at 25 degrees Celsius or 95 degrees Celsius? So if we look at this equation, delta G equals delta H minus T delta S, we've used this equation a lot in the course of this entire exam, including the multiple choice. That checks out. This is a pretty important equation for this unit. Delta H is positive. We just calculated that. And delta S we also predicted to be positive. So we have a positive and we're subtracting a positive. If we want delta G to be negative, because negative means favorable, we want to raise the temperature. we want to make this second half of the equation bigger than the first half of the equation, because if we're taking a positive and we're subtracting a positive, if that second positive is bigger, then we're going to end up with a negative. So we want to raise the temperature so that this second half of the portion is the bigger positive and we end up with a negative. So the answer is 95 degrees Celsius. So we want 95 degrees Celsius. And to justify this, it helps putting this, because if you're doing that, the grader kind of knows you're thinking about it correctly, but let's just write something. If delta H and delta S are positive, the reaction is favored at high temperatures. And I've seen this phrasing used a lot in like official answer keys or scoring guidelines. So that T times delta S is greater than delta H. So that's a good way of saying what we kind of just visualized using this equation up here. The student runs the reaction using the 3 to 4 mole ratio of silver to nitric acid. Suggest a method the student can use to isolate solid silver nitrate from the system. Okay, so this is really just like a laboratory methods type of question. If we use a 3 to 4 mole ratio of silver to nitric acid, notice that that's just our ratio in the balanced reaction. It's a 3 to 4 ratio. What that means is we are using the perfect amount of both things so we don't end up with any limiting reactant. We don't end up with any excess reactant. We're just going to react to completion. We're not going to end up with anything else. Notice what's in our products. We have gaseous NO, liquid water, and aqueous silver nitrate. So if we want to get solid silver nitrate, what this question is asking, we're asking how do we get solid silver nitrate? If we just take this, we run the reaction, and we just allow the reaction to sit around a while and evaporate, or we heat it up and we encourage that vaporization more, we are only going to be left, once all the liquid evaporates, we are going to be left with just solid silver nitrate. Why? Okay, well, NO is already going to be a gas. It's already going to go away. Then we're left with just silver nitrate, aqueous, and water. If we evaporate the water, okay, the water is now going away when we evaporate the water. And that turns the aqueous into solid because all the water is gone now. If we evaporate all the water in an aqueous solution, the ionic compound has no choice other than to just reform the solid. So that's what the answer is, just allow the water to evaporate completely. And that's it. All right, that is the FRQs. I hope that was helpful. I wish I had my scoring guidelines so I can tell you the point values, because I get the sense that like this guy was a 2-pointer right here. Let's count up the points, make sure I got them all. So 1, 2, 3, 4, 5, 6, 7. Or there's 7 parts, right? 1, 2, 3, 4, 5, 6, 7, which means 3 of the parts needed to be 2-pointers. My guess would be F was a 2-pointer. My guess would be D would be a 2-pointer. And I would also guess, I don't know, it would be the last 2-pointer. It could be C, it could be E, it could be G. I wish I knew that, but I don't. All right, that is it for this one. Good luck with the rest of your studying, everyone. Let me flip my laptop back around. All right, that is all from me. See ya.